Is everybody there? Hello? I don't know what's going on. Okay. Can you hear me?
Yes, we can hear you.
Oh, okay. Oops. Okay, you can hear me then. Good. All right, wonderful. All right, very good. Thanks very much. I don't know why I couldn't hear you responding back, but that's just fine. So very good. Okay. Now, basically what we're going to do now is essentially continue where we left off. I was telling the other students I graded the exams. Basically, they weren't what
Did he leave? Oh no, there is. Okay. What's going on?
we got disconnected, so I'm sorry about that. So as I
Yeah.
was saying, the way this is going to work is you did well, reasonably well, based on other schools, pretty well on the multiple choice portion of the exams. I'll have them finished probably by Wednesday, but my promise is for all my students to get them done within a week. But I'm going to be working on them this afternoon and tomorrow, so don't worry. And the way I'm going to work it is also in other universities and colleges, I have kind of dropped the first test if people do better on it, and then do better on the rest of them. And so basically, I'm not allowed to do that here. So basically, they'll all be included, but I do have some limited ability to modify things as we go through the semester. So the important thing is to know what you do at the end of the semester. And please don't worry about the process, because it's all about learning your mistakes, etc. Okay? So I hope that makes sense to everybody. All right, now what I'm going to do now is continue kind of where we left off, but what I want to do though is use Hein as the representation of this, just so we can go through it in a little bit more simple process regarding the nature of how these reactions are done. So basically, the key thing is the way this works is if you go it step by step, kind of like a little boy or girl learning how to walk. Eventually they crawl and then they get up on their things and then they start trying to walk around or whatever else. I got to see my granddaughters gradually learning to walk over a period of months. And so it's a very fascinating process, but obviously you're learning to walk intellectually here. So again, it's a kind of thing where I ask you all to be patient with yourselves, and I do want you to understand what's going on regarding the nature of these. So what we're going to do now is continue where I left off, and first have a short review. I'm using Hein here because he goes very well into the whole material, and it kind of puts everything into context regarding what we've been doing so far. And it's a very good PowerPoint, and I highly recommend you use it to go over for yourself when you're working on the homework problems. And I will have some more worksheets and such like that for you to work on for Wednesday as we continue. So what I'm going to do quickly is go through this review and go through the process, grams to moles to moles to grams, and then we add the one more step of the limiting reactant, and then essentially we're done. So I hope you all understand the logic as to what we're doing with this. So let's move forward here. Okay, and the molar mass of the element is its atomic mass in grams. Okay, so for example, if we have chlorine, it is normally in that form. So what will its molar mass be for chlorine gas when it's in that form? Huh? Yeah, 35.5 times 2, or 70.9. Okay, and it's a fraction because of all the different isotopes in there. So it's important to keep that in mind as well. Okay, with the other elements, for example, silicon, and I'm looking at the, let's just go with sodium. Sodium is monatomic, and basically that's 22.99 grams per mole. So basically the key thing to understand about the nature of how this works is that it's a very logical thing of putting the pieces together and getting the molar mass. And that's the number of atoms in the element. The molar mass of an element or compound is the sum of the atomic masses in all its atoms. Okay, so what is the molar mass of this? This is sugar. What's the molar mass of that? It looks complicated, but it isn't. Well, what do you start with? Carbon, right? So you have 12 times 12, which equals 144, okay? Hydrogen is what for each one? 1. So we have 22 times 1, 22. Oxygen is 11, so you have 11 times 16. 16 is the one for oxygen, okay? So you have 10, and so it's 176. You add them all together, you get the molar mass, okay? So it's a very simple process. The molar mass is the grams of the monatomic element over the moles of the element, or when you're talking about a molecule, it's the whole molecule together. And the number of moles divided by the mole, whatever the definition of the mole is. So for example, the mole is a relationship going from atoms to the molar mass, okay? And so basically it's very, very good to understand how this works. Now, the first thing for calculations of a mole mass volume relationships, the chemical equation must be balanced. So let's balance something very simple. Hydrogen plus oxygen goes to water. Is it balanced? No. So what do you have to do? Go back and forth. How many hydrogens on the left? 2. How many on the right? 2. How many oxygens on the left? 2. How many on the right? 1. So you put a 2 in front. That changes the hydrogens. The 4 on the left, you got to put 2 on that side. So we went back and forth or whatever. That's what you did over the weekend. Practice that, okay? And I'd like you to check your work when you look in the key this afternoon when I put the key up. Okay, hopefully you all did it and we're ready to turn it in. But I think it'll be very useful for us to do that. Now, are there any questions from the sheets that you'd like me to balance something of the sheets you did for today? Any questions of something you didn't understand? Sure. Can you drop your mask so I can hear you better?
I was confused on the last one of the last question.
Okay, so what is it?
C5H8O2
C5H8O2
plus NaH
NaH
plus HCl,
plus HCl, okay?
and then yields C5H12O2
Okay,
plus NaCl.
plus NaCl. Okay, all right. Now, C5H12O2, correct?
Yes.
Okay, all right, so sorry, we got disconnected. We'll go back to the shared screen again. Okay, so here, how many carbons are on the left? How many on the right? 5, okay? So we can't really use that one. How many sodiums are on the left? 1, and we have 1 chlorine on the left, and it's 1 on the other side, okay? How many hydrogens on the left? 10. How many on the right? 12, okay? So there it's a little bit more complicated. So how many do you have to add? 2. So what we could do is put a 2 in front. Oops. So we could put a 2 in front like that. Oops, wait, go back. We could put a 2 in front here, and we put a 2 in front there. So what happens is you get a 2A and ACl. Now how many hydrogens do you have on the left?
Why did you put a 2 in front of both?
Because you need 2 more hydrogens, right?
But would that be 4 more hydrogens?
No, we just put a 2 in front of both because it's NaH and then you have HCl, right? So basically you just want to add 2 more. So we just put a 2 in front of both. And that changes the sodium and the chlorine, right? So then you have to change that one. See? When you add the 2 to both of these, this makes this 2. So it goes down to there, okay? So now you have the correct number of hydrogens on the left, and you have the correct number of hydrogens on the right. How many oxygens are on the left? 2, and you have 2 on the right. So it's done. So it just looked more complicated than it was. Did you follow my logic?
Yeah.
You want me to make it bigger?
No, I get it.
Okay, did everybody get it? Okay, so again, it's just a matter of, even though it looks complicated, you just go back and forth until it works, and then you add a little logic in there and kind of figure it out, okay? And that's a more difficult one. I'm not likely to give that on the exam, but the point is, again, it's a good illustration, okay? So let's go back to this. I'll erase the slide now. Okay, so it must be balanced. So let's start with this one. Is that balanced? No. How many aluminums on the left? How many on the right? 2. So you got to put a 2 in front. So you got to put a 2 over here. Oops. Okay, now the equation is balanced. Once you put a 2 there and you got a 2 iron, now it's balanced. So basically that's a simple process to do it. We just put the 2 aluminum in there, figured out what the iron is, and then added the 2 in that, okay? So you first was that. The number in front of the formula represents the number of moles of the reactant or the product. Okay, so essentially you have the 2 related to it. Now, the mole ratio method. This method is fabulous. When I taught Intro to Chemistry, I used this book and used other books like it, but basically the students really understood it very quickly. I think we spent a whole week on this section, this chapter, essentially going over the individual process. But we're just going to summarize this today using what you already know. Okay, so it's the mole ratio method. It's the area of chemistry that deals with the quantitative relationships between reactants and products. The mole ratio is the ratio between the moles of any 2 substances involved in a chemical reaction. The coefficients used in the mole ratios are derived from the coefficients. Okay, and basically some examples. Okay, if you look at these things related to it, what are the different mole relationships that you can get from this? This is balanced, so let's keep this simple. How many moles of hydrogen are required to react 1 mole of nitrogen? 3, okay? How many moles of ammonia can get as the reactant from when you have 1 mole of nitrogen? How many moles of product do you get, the ammonia? 2, okay? So there's a 2 to 3, there's a 1 to 3 relationship first. There's a 3 to 2 relationship. There's a 1 to 2 relationship, and you can get these different relationships here. Like this is the 1 to 2 relationship. This is the 3 to 2 relationship. This is the 1 to 3 relationship. So you can get all these different relationships, and that's the way you convert the numbers you convert one thing to the other using the balanced equation, okay? So it's just a matter of going through and seeing all the different relationships there. So if you start off with 6.5 moles of hydrogen, okay, in a problem, you have 6.5 moles of hydrogen, what cancels out? In this equation, what cancels out? Yeah, the moles of hydrogen. And now you have the number of moles of nitrogen that are needed to react with it. Okay, so basically that's a problem that you might be asked, some sort of relationship like that. So essentially, we're kind of putting the pieces together to try and understand the nature of how these things work. Okay, so now we continue with this. Okay, the 1 mole to 1 mole relationship there, the 1 to 3 mole there, and you have these other relationships, 3 moles to 2. Okay, so basically, if you have like this 3 moles of hydrogen produces 2 moles of ammonia, and a sample problem might be this, and because it's equal to 1, if you have 6.5 moles of hydrogen, how many moles of product are you going to get? Well, you invert this. So 3 moles of hydrogen gives 2 moles of ammonia. Okay, what cancels? The moles of hydrogen, okay? So now you've essentially gone one side to the other. You've crossed the barrier between reactants and products. So now you can figure out the moles of ammonia. If you want to determine the number of grams of ammonia, what would be the next step? Brendan, what would be the next step? You go to grams of ammonia. Correct. So ammonia, it's 17, 1 mole of ammonia is 17 grams of ammonia. So now you just do the math. And now you have how many grams of ammonia you got from 6.5 moles of hydrogen. Okay? So essentially we answered the question, yes.
So I understand the process, but where would you get the 6.5 moles of hydrogen?
That's in the problem. So say, for example, you're asked, you have 35.3 grams of hydrogen. You're reacting with nitrogen to form ammonia. How would you do that? 35.3 grams of hydrogen. You're reacting it with yeah. Say you have 35 grams of hydrogen, 35 grams of hydrogen. You're reacting it with nitrogen to make ammonia. How much ammonia could you form? What extra step is in there?
Finding molar mass.
Well, yes. And so essentially we have 35 grams of hydrogen, right? So what do you have to do first?
Find the molar mass of ammonia.
No. Let's go back to the original thing. What you have grams of hydrogen. That's one of the reactants. You want to convert it into moles of hydrogen, right? So what do you use?
You're going to use the molar mass of hydrogen.
Correct. So it's 2 grams of hydrogen is 1 mole of hydrogen, right? Okay, so grams of hydrogen cancel. Then you proceed the way we just showed you. Okay, so that's a sample problem that might happen. Okay, and it's just adding a little step there. And again, this is the 3rd floor. Did anybody jump in a symbol bound up to here, this 3rd floor? No, you all walked up the steps. Well, here we just added one little step at the beginning to change grams of hydrogen to moles. Okay, but again, this process really works. And if you can understand the logic, you could do almost any problems shown at you. Okay. So basically the mole ratio is used to convert the moles of one substance to the corresponding number of moles of another in a stoichiometric problem. That's essentially going from reactants products mostly. Or it could go from reactant to another one to determine how much you need. Okay, so essentially you could do that. The mole ratio is used in the solution of every type of stoichiometry problem. First, you convert the quantity of the starting substance to moles if it's not already in moles. Okay, so basically what we're going to do now is essentially I'm going to take 35 grams of sucrose, C6H12 of glucose, reacts with oxygen to form carbon dioxide and water. Okay? So what's the first step you have to do? Balance the equation. Yes, you got 6 carbons on the left. How many on the right? 1. So you put a 6 here. How many hydrogens do you have on the left? 12. How many on the right? 2. So you put a 6 here. How many oxygens on the right now? 6 times 2 is 12, plus 6 is 18. So you have 6 there, which is already provided. And so now you need 12. So basically you'll put a 6 there. So now you know the mole ratios between them. Okay, so you start with 35 grams of that. Well, 35 grams of C6H12O6. Okay, what's the first thing you do? And I'm just going to draw it out like this. What's the first thing you do? Convert to moles. So C6 is 72. 72 plus 12. 72 plus 12 plus 6 times 16 is 96, just to keep it simple there. So we have 84. We have 84 plus 96, so that is 180 grams, okay? So we have 180 grams of C6H12O6 is 1 mole of this C6H12O6. What cancels? Grams, yeah, very good. Okay? So now, the problem asks, how many grams of water you get. So let's go to the next stage. What's the mole ratio between the moles of C6H12O6 to moles of water? 1 to 6. So we have 1 mole of this, C6H12O6, gives 6 moles of water. Okay, this cancels. So what's the next step there? To convert to grams, and so that essentially you have 1 mole of water. 1 mole of water, H2O, is 18 grams of water, and that's on the end of this. And so moles of water cancel, and you now do the math. Okay, so we've essentially started with reacting 35 grams of glucose with oxygen. Yes?
How would that question be worded? Like, would it say like how much water or how many grams of water is given?
Yeah, how many grams of water? Or what's your first name again? Sorry. Paige. Paige, you ate 35 grams of glucose. How much water did you give off due to that reaction? And I'm talking biochemistry here, but is it really any different? No. Your body is an engine. It burns it, okay? You breathe in the oxygen, so it's the same thing. That's the beauty of chemistry, is it works across, okay? And it's just like burning in a fire, burning glucose in a fire or whatever else. Now, how do you think they figure out how many calories are in a cookie? Well, they burn it in oxygen, okay? They burn it in oxygen, figure out how much heat comes off of it, and convert it into calories, which then they make the kilocalories, which is essentially the food calorie thing. So essentially they burn it to do it, But your body, when you eat the cookie, burns the cookie also. You get the energy in the form of converting it as well as the energy from that to keep your body warm. Okay, so essentially they work together there. Okay, so it's kind of cool how it all works together, even those of you interested in biochemistry. Okay, that's why chemistry is so important for biology. Okay, and a lot of people don't understand. I've had many biology majors over the years say, Dr. Douglas, why do I have to learn this stuff? I don't like chemistry. Why do I have to learn this? Well, this is part of why. Okay. Okay, convert the moles of starting substance to the moles of desired. So that's essentially going off. Okay, so essentially we have convert the moles of desired substance to unified steps in the problem. So let me give the thing again. You start with grams, you go to moles, okay, and then you go, this is reactants, just like the chart in the other one, then go to moles of product, and back to grams again. So again, you're learning little steps, okay? Determine the moles of this thing. So I'm not going to draw on this letter, we'll just use their examples. So starting substance to moles.
Go back 2 slides.
Yeah. Well, you'll have a copy of this. You don't need to write it down. I'm going to share, I'm going to save it in the share drive so you can go back to it. But I want you to see the process here. I'm just going to spend 20 minutes going through the process, okay? So here we start the substance, moles to grams. This is a conversion that I did in the previous example, okay? Starting substance to moles. How many moles of sodium chloride are present in this amount of grams of sodium chloride? The molar mass is 58.443. So how would you determine that? And to save you have to deal with my bad handwriting, I'll just use the slide. Okay, so let's go through this. Moles go to grams. Okay, so the first thing, what do you do to determine the number of moles? Well, you plug the grams in here. Okay, 58.4, no, sorry, we have 292.215 grams of sodium chloride, right? In the problem. The molar mass is 58.443 grams of sodium chloride. Okay, moles of sodium chloride. Grams of sodium chloride cancel. That'll calculate the moles. That's the calculation you're going to have to do for chapter 3, okay? And what you did for chapter 2 earlier, okay? So essentially we got that set up like that. 5 moles of sodium chloride are in that. Okay, and basically you have the things. Determine the mole ratio of the desired substance to the starting substance. So essentially you go, that is the other one. The number of moles of each substance in the biology equation is indicated by the coefficient in front of each. So use the coefficient to set up the mole ratio, just like I did in the previous example with the sugar, with the glucose, okay? Determine the mole ratio. Okay, essentially we have there. Okay, the mole ratio is the moles of starting substance across. Okay, determine that, multiply the number of moles of the starting substance by the mole ratio to contain the number of moles of the desired one. So let's just start with something simple again. You've got hydrogen plus oxygen goes to water. H2O, 2, okay? So that's balanced. The number of moles of the starting substance for step 1 from the number of moles of the desired substance. You're trying to get water. What is the mole ratio between the hydrogen and the water? It's 2 to 2. So if you start off with 68.4 grams of hydrogen, okay? How many grams of water are you going to get at the other side? Grams of water. Okay, how would you calculate that? Convert 68.4 grams of hydrogen to what? To moles. Yes, very good. Okay. And then you go through the process. Okay. So I'm not going to try and write on the slide with that. I'm just going to erase it now. And we'll use the thing with this. Okay, so you start with the moles of desired substance in the end. From step 1 there. In the following reaction, how many moles of lead chloride are formed if you have 5 moles of sodium chloride reactant? Now they showed you here, you have the balanced equation already formed. So what is the mole ratio between the lead chloride and the sodium chloride? How many moles of sodium chloride are required to get 1 mole of the lead chloride? 2 to 1, yes, very good. Okay, so let's do that. Moles of desired substance there. You start with the moles equals 5 moles of sodium chloride. Well, you use this mole ratio again. This moles cancels with that one. That tells you how many moles of lead chloride you need. Or you get. I mean, that's the amount of, essentially, that's the amount of lead chloride you get. 2.5 moles. Okay? So again, we started with a certain amount of sodium chloride. You end up with the other. So again, it's going from one side to the other. Again, in a nice process. Calculate the desired substance and the units that specified in the problem. If the answer is to be moles, the calculation is complete. But if it's in grams, you got to convert to grams again from the moles. So sometimes the answer is in moles, other times it ends up being in grams. Okay? And basically what I'm going to have also on Wednesday to kind of do this is we'll have the last 20 minutes of class be a quiz where I go over this process with that, adding a little extra step of the thing in it. So basically, this will be an in-class quiz, and you folks online, I will post it. At the same time, I would like you to do it for yourself. I'm not going to grade it, but I'd like you to do it for yourself, just to go through the process yourself, and you fix it yourself. So basically, I'm going to have the students here do it in class, and then we'll look at it before we leave. And the other students, you can do it too. I will post it. So you can do it during the virtual time, and then we can, in the last 5 minutes, we'll go over it, okay? Something like that. So it'll be like a little work thing to do that. Okay, so for example here, you've got 90 grams of water. To get that, you want to convert it to moles of water. Okay. Essentially grams of water, from moles of water to grams of water, what you want regarding to calculate the number of grams, you essentially want to convert it to the other sense once you have ended that material. So calculate the desired substance in the unit specified in the problem. And please don't worry about this kind of problem, because I'm not going to have you do I'm not going to ask you how many atoms are required. That's kind of silly. That's more another extra step I give to intro to chemistry students, just to understand the math a little better. So calculate the units there. Now mole to mole calculations here. Phosphoric acid is one of the most widely produced industrial chemicals in the world. Most of it involves the wet process by where you get phosphate rock with sulfuric acid. Okay, and it's a very cool process. So essentially it looks like this. You got the phosphate rock reacting with sulfuric acid, gives phosphoric acid plus hydrogen fluoride plus calcium sulfate. Calculate the number of moles of phosphoric acid formed by the reaction of 10 moles of sulfuric acid with this. So basically, we're going to do the number of moles of phosphoric acid. So you're given 10 moles of sulfuric acid, right? So 10 moles of sulfuric acid, H2SO4. Okay? the number of moles formed of that. So what is the mole ratio you use? 5 to 3, very good. 5 moles of sulfuric acid, H2SO4, gives 3 moles of phosphoric acid. Moles of that cancels, you now have your answer. That's again going across the thing. You start on this side, it goes across to that. So if you have a thing like looks like this, we've essentially gone across the barrier. The first one is grams. This is now moles of reactant, and this is moles of product. Okay, and then you go grams there. So sometimes you get a problem and you just go from there to there only. Sometimes you go to a problem that goes all the way to there. Sometimes you get a problem that goes all the way. That's the nature of those kind of problems because you have different reasons for having those different kind of relationships. So let's continue. So essentially go there across it. Now I'm going to go relatively quick because I want to get to the last part. Calculate the number of moles of sulfuric acid that react with 10 moles of this. Okay, so essentially you have there. Okay, again, the mole ratio there, you go through it, use the conversion there. 10 moles of calcium phosphate. 1 mole of calcium phosphate requires 5 moles of sulfuric acid. So basically, that'll give you how many moles of sulfuric acid are required for that reaction. So essentially, they've stayed on the reactant side with that problem. And it's just, again, that. So molar mass calculations, you start with that, you convert it to moles, you use the mole ratio to convert it there. Some examples, calculate the number of moles of sulfuric acid to give 784 grams of phosphoric. So what's the first step? Yeah, grams to moles of phosphoric. Then use the mole ratio again. Okay, step by step. Convert the grams to moles there. So you got that. You convert it to moles of phosphoric acid. Then use the mole ratio there by the mole ratio method. That gives the amount of product you have. Does everybody follow the logic there? Okay, so you continue. Calculate the moles necessary to yield there. The continuous method, the conversion there, grams to moles to moles. So essentially you go grams to moles to moles. That's going three places across the thing. So if I give my pointer again like this, you have it go like this to that, okay? Using the mole ratio there. Calculate the moles of grams required to form 12 moles of ammonia. Okay, you want 12 moles of ammonia, right? So essentially what you start with is you're going back the other way. You're essentially going back this way and then going back to the hydrogen on this side. So here you're starting with the 12 moles of ammonia and going back. So essentially go step by step. 12 moles of ammonia, calculate by the mole ratio method. You have 2 moles of ammonia, requires 3 moles of hydrogen. Okay, 18 moles of hydrogen, then you convert it to grams. So essentially I'm going back on the thing, go back the other way. So essentially you're learning how to go down the stairs instead. I don't know why it's upside down. Okay, but calculate the number of grams required to form 12 moles there. The continuous method there with that. Continue going across, that'll give you 36 grams of there, again, with the continuous method. And that's what I like doing, is having the line in there. You can see it for yourself with the barriers like that. Mass to mass calculations. Now this is going this way like that, okay? So solving mass requires all the steps in that. You start the substance to moles, the mole ratio, then to go to moles of reactant to moles of product, then you convert to mass. Calculating the number of grams formed by the reaction of 112 grams of hydrogen. So let's start with this. 112 grams of hydrogen. So what's the first step? Convert to moles, good. So 2 grams of hydrogen is 1 mole of hydrogen. Okay, what cancels? Grams of hydrogen. Okay, so now you go across the barrier again. 3 moles of hydrogen, okay, gives how many moles of ammonia? 2 moles of ammonia. Okay, so moles of hydrogen cancel. Okay, then you go to the molar mass of ammonia. 1 mole of ammonia is 17 grams of ammonia. And all that's left is the math. Okay, so essentially what we did is we started this side, we went across and then went to there. We started grams, going to grams on the other side. That's going across the whole thing. Now, let's try something different with this. Okay, you have, say you have 112 grams of hydrogen, and you react it with 34 grams of 134 grams of, let's look at nitrogen on here. No, 28 grams of nitrogen. 112 grams of hydrogen, and you react it with 28 grams of nitrogen. Okay, and basically you want to know how many grams of product you get of ammonia. Okay, so let's try that. Well, we got the first part done. You got the 112 divided by 2 there, and you can calculate the math. Because anybody have a calculator? Can you calculate that out quickly, please? 112 times 2 times 17 divided by 6. 112 times 2 times 17 divided by 6. What do you get? 34.6? 634.6 repeating? Okay, good. So that's how many grams you get if you had the proper amount of nitrogen, okay? But you have 28 grams of nitrogen. Is it possible to get that much product? You have, using the formula there, you're supposed to get 634 grams. So you're supposed to get 634 grams, 0.6 grams of product of ammonia. Is it possible to get that if you have 112 grams of hydrogen and 28 grams of nitrogen? Is that possible? No. What is the limiting reactant? The nitrogen, yes. So essentially, you do the same problem using nitrogen, 28 grams of nitrogen, and I picked nitrogen grams easy that way. So if you look at nitrogen there, it is 14, so 28 grams of nitrogen is 1 mole of nitrogen. So you use the mole ratio then, 1 mole of nitrogen, 1 mole of nitrogen gives you 2 moles of ammonia.
Wait, but aren't you supposed to start with the same amount of grams for each?
Well, you could, but I'm doing a limiting reactant question. I've only got 2 minutes left in class. I changed the thing to say you're reacting it with 28 grams of nitrogen. Okay, so this is limiting reactant question. So basically what I'm going to ask you to do is continue the slides later and go through that, and you'll see the process. There's only 20 slides left in this, but it goes through the rest of it. But let's do the calculation first before you leave. Okay, so what cancels out here? The 28 also does, so you can cancel that out. And now you have that, and you convert this to 1 mole of ammonia is 17 grams. So how many grams of product are you going to get? So the only thing you're going to get is 34 grams of product out of that. That is the limiting reactant. Okay, that's the only difference. If you do them with both of them, you'll get the answer to the question about what's the limiting reactant and whatever else, okay? So basically, I'm going to delete what's on the slide, and you can see it in the video. Or maybe I'll just keep it what's on the slide just to, yes.
How do you get the 2 moles of ammonia?
What, sorry?
Where did you get the 2 moles of ammonia from?
That was just from the 28 grams. We reacted 28 grams of nitrogen with it, and the 2 moles of ammonia came from this ratio, 1 to 2. 1 to 2 here, okay? Do you see that? Okay, so that's where it came from. So I'm going to delete the slide, and then you can see it. But basically, it's just go step-by-step process there. And you can get the number of mass like that. That gives you the product, and then moles to grams there, and then 629 grams, okay? But we changed the formula a little bit. And then the continuous method like that, okay? So I'd recommend you do the continuous one. And the last 20 slides of this is going into limiting reactant, but I don't have enough time to do it today. So basically that's kind of where we're going. And that's why I added the additional thing of having 28 gram, sorry. That's why I had the extra one of 28 grams of hydrogen in, sorry, of nitrogen in it, 28 grams of nitrogen in there. Yes.
For our lab,
Yes.
because I'm group 2, they don't come in tomorrow, I came to my lab today with you.
Well, just put it in my box outside things, okay? Yeah, you're virtual tomorrow. You're not, okay, yeah, we don't have lab this week for your group, okay? Okay, we're done for today. Thank you very much.
You want us to use it?
No, I want you to use it and then look and check your work with the key that goes up, okay? Yes,
This is Andy's lab report. Just in
so
case-
put it in my
in
box.
your box. Okay.
Yeah, that's fine. Okay, are there any questions of those of you who are distant, virtual? Any questions? Please continue. Any questions? Okay, I will put the slides in the Hind folder, so you can use that to finish the slides, but hopefully that'll help you understand the nature of what the end of this chapter is all about. So have a good day. Thank you. Bye.